Welcome to clickmyproject.com. Let's discuss about the product. Our product is a Colpitts CMOS Quadrature VCO using direct connections of substrates for coupling. A new low phase noise low power quadrature voltage controlled oscillator, that is called QVCO, using differential Colpitts oscillator is presented in this process. The proposed QVCO is composed of two identical current switching differential Colpitts VCOs, in which the first core VCO is coupled to the second in an in-phase manner, and in the second core VCO is coupled to the substrate of cross-connected transistors as well as the substrates of MOS varactors, which are used in alleviating the need of any extra elements for the coupling, which could not add noise and increase power dissipation. A linear analysis is presented that confirms that the proposed circuit generates quadrature waveforms. The proposed coupling techniques can be generalized to n differential Colpitts VCO for multiphase signal generation. To improve the phase noise, various experiments are done in previous methodologies, which modifies the coupling networks. The coupling design is presented in and it is applicable to n number of differential Colpitts QVCOs for multiphase signal generation process. The quadrature VCO is combined with two similar current switching and differential Colpitts VCOs, in which the first core VCO is connected to the second in an in-phase manner, and the second VCO is connected to the first in antiphase manner. For this connection, the substrates of the interconnected transistors as well as the substrates of MOS varactors are used here. In conventional cross-connected LC VCOs, the noise generated by the active components perturbs the VCO output as their zero crossing, that is the maximum noise sensitivity point. On the other hand, in Colpitts oscillator, the maximum noise level, that is the maximum number of impulse sensitivity function generated by the core transistor, is aligned with the minimum oscillator sensitivity point. Thus, Colpitts oscillators have superior cyclostationary noise properties and, as such, potentially a better phase noise performance compared to the conventional cross-connected LC VCOs. In recently reported QVCOs, differential Colpitts oscillators have been replaced with the cross-connected oscillators, thus achieving a lower phase noise. In two complementary Colpitts VCOs are completed and coupled to each other via four parallel coupling transistors. However, parallel transistors dissipate power and can degrade the phase noise of the QVCO. Let's see the block diagram of our process. So this is the functional block diagram as per the designing methodologies. As we already discussed, our designing methodology of the system is based on CMOS designing. For this CMOS designing, we have to use Tanner EDA tool, and at the Tanner EDA tool we are implementing this product methodology, and initially we have to design the VCO. So according to our modification, the second core VCO have to modify the overall circuit, and for the overall circuit we are applying the gating which is clocked, and finally from the overall design we are obtaining the simulated result through the Tanner EDA at the waveform edit, and finally from the obtained wave edit we have to see and verify the performance report. Let's discuss something about the tool. For this CMOS design based methodologies, we have to use CMOS design tool, that is called Tanner EDA tools. Commonly, Tanner EDA tools having lot of subdivisions, that is called S-edit, L-edit, W-edit, and such more. There are lot of under devices. So in this we are using S-edit for circuit designing. So and then after we design that S-edit, while simulating, the circuit's design will pass through the T-space that we can understand through the checklist generated through the spice code. And finally, while we are simulating, the timing diagrams will appear in WEdit. Hence, commonly for our CMOS based designs, we will use mostly these three edit things. That is, again I will say as SEdit, LEdit, WEdit and T-space. So, we can design the circuit based CMOS transistors by using SEdit. Here, before we starting the simulation, we have to select a new cell. Here is a cell menu. Here we have to select the cell menu and we have to select new cell. So there you can select number of cells like cell 0, cell 1 up to cell n you can select. So each cell should contain different CMOS design. And next process is to set up simulation. Here this icon, while you are pressing that will leads you to setup simulation. In the setup simulation you have to set up maximum time duration for the design and nanoseconds based setup methodologies. After designing setup designs, we have to load the library files. So initially for the design of CMOS designs we need some CMOS components. Those CMOS components will occupy in CMOS libraries. That means CMOS libraries contains components of which required for CMOS design. So here you can see what are the components listed in CMOS library. While you are pressing add, it will leads you a window menu. There you can locate the library file where you have stored. So from the location where you have stored, you can select all components which you can need for your CMOS design. So after design of this cell, you can save the design, and while you are pressing run, it will leads to T-space. So through T-space you can see what are the checklists available in T-space. In T-space usually the components which you have used are listed in as a component code. That means you can see that as a program wise. That's why that T-space codes are called netlist. You can run either from SEdit or from T-edit. From wherever you are running, the output timing diagrams will show in WEdit. In WEdit you can see the waveforms which we have obtained for corresponding CMOS design. And also you can clarify what are the result parameters, and you can measure all the parameters which you need for the design from the WEdit. Thank you.